Hello, I'm Dr. Pariser, and it's Wednesday, July 22nd, 2009, and I'm going to talk about the derivation of the electromagnetic wave. Specifically, this is a course PHY 201, and it's a second term physics class, and there are two papers that are available to the students. They're on the web, and students have downloaded these papers and have them as reference. I'll begin by saying that Maxwell, who lived in the 1860s, who did his work in the 1860s, was concerned about the sun and the earth. And what Maxwell found was the electric constant and the magnetic constant predicted the speed of light. So Maxwell said that light must travel as an electromagnetic wave. And so Maxwell added this term. These became Maxwell's equations. What I'm going to do for the derivation is I'm going to use Faraday's law. This is Maxwell's equations in the differential form. This is called the divergence of the electric field is equal to the charge density over the electric constant. This is divergence of the magnetic field is equal to 0. This is the curl of the electric field is equal to the negative partial derivative with respect to t of the magnetic field. And the curl of the magnetic field is equal to the electric constant times the magnetic constant times the current density of the electric constant plus the derivative of the electric field with respect to time. And to begin with, the question is, in this room, if you turned on a television set, you would see the television program. So Maxwell had to formulate his equations in a differential form. And in the differential form, this is how they look. And starting over here with Faraday's law, if you take the curl of the electric field, then you have to take the curl of the magnetic field. And the curl of the electric field is equal to this. Now the curl is the del operator operates on distance. This operates on time. So if you push this through, you have the curl of the magnetic field is equal to minus the partial derivative with respect to t of the magnetic field. Curl of the magnetic field. And why do you have that? Because the magnetic field is here. By making this substitution, this is a vector identity, which is the gradient of the divergence of the electric field, minus the Laplacian in the electric field, is equal to the negative partial derivative with respect to time of the electric constant, magnetic constant, partial derivative with respect to time of the electric constant. Now this is the wave equation, and if you look at a differential equation book, it's a famous equation. The Laplacian squared, the Laplacian in the electric field minus the electric constant times the magnetic constant is equal to the second partial derivative of the electric constant. Now, to get a solution for a second order differential equation, you guess. And what we're going to do is guess a wave. This is called an eigenfunction. And if the wave is a cosine wave, the amplitude would be E, and the maximum length would be, wavelength would be where theta was equal to 2 pi. Now the top of the wave, if this is theta and we have a wave omega t minus kx, then if we wanted to stay at the top of the wave, this would have to be equal to 0. So if omega t minus kx equals 0, then omega t equals kx, and omega over k times t is x. So this is a wave that is propagating in the x direction. And omega over k is 2 pi times the frequency over 2 pi divided by the wavelength. And that's the frequency times the wavelength. The frequency times the wavelength is equal to the velocity of light, the speed of light. Now, taking that and putting that into this equation, we take the derivative with respect to x of this function. And this function varies with x, and the derivative of the cosine would be minus the sum. So we have e sine omega t, there's a minus sign, and when you take the derivative with respect to x, there's a minus k. So there's a minus k e sine omega t minus kx. And if you take the derivative with respect to y, it's 0, because there's no y. If you take the derivative with respect to z, it's 0. But this does have a derivative with respect to time. And the derivative with respect to time is going to be minus e sine omega t minus kx. And the derivative with respect to time will pull out an omega. And if you bring it down and take the second derivative, then you had a minus sign, you have a minus k squared e cosine omega t minus kx. And over here you have epsilon 0 mu 0 omega squared e cosine omega t minus kx. Now, this one became a plus by the second derivative, and this one is minus. And so if you factor out this, you have this term times this term is equal to 0. When two things are equal to 0, either the first is equal to 0 or the second. If the first is equal to 0, then it's not a solution because the electric field is equal to 0. So if this is not equal to 0, this must be equal to 0. And now I'm going over here. If you say that this eigenfunction has eigenvalues, these are eigenvalues, and these have to be equal to 0. So epsilon 0 mu 0 omega squared minus k squared equals 0. So if you bring k squared to the other side, epsilon 0 mu 0 omega squared equals k squared. If you divide by k squared, you have epsilon 0 mu 0 omega squared over k squared equals 1. If you divide by epsilon 0 mu 0, you have omega squared over k squared is 1 over epsilon 0 mu 0. And if you take the square root, you have omega over k equals 1 over the square root of epsilon 0 mu 0. Now this is the speed of light. And this is 3 times 10 to the 8th meters per second. So omega over k is equal to the speed of light. Now omega over k is the frequency times the wave. And now the question is, now that we have a solution for the wave equation for the electric field, can we find a solution for the magnetic field? To find a solution, we go back to the original equation. Faraday's law. The curl of the electric field is minus the partial derivative with respect to t of magnetic field. The curl is equal to this determinant. This is ijk, partial derivative with respect to x, partial derivative with respect to y, partial derivative with respect to z. E sub x, e sub y, e sub z. Now, when you evaluate a determinant, you put down, you add the next two columns, I, partial x, partial with respect to x, e sub x, and j, partial with respect to y, e sub y. And you evaluate by multiplying along these diagonals. And you get all of these terms. Now, in the initial condition, we said that we have an electric vector in the y direction. So the electric vector in the x direction and z direction are 0. So all the terms that have z's and have x's go to 0. Okay? So when you do that, what about the derivatives? If the derivatives are with respect to x, then you can have a value. If they're with respect to y and z, they're not going to have a value. So over here, this is the only term that's non-zero. Now, if you do this, you say the magnetic field is going to be in the z direction. And I should say to you that mathematicians love this, but physicists don't. So physicists like it this way. This is the electric field, this is the magnetic field, this is the direction of propagation. So in our case, if the direction of propagation is in the x direction, the electric vector is in the y direction, then the magnetic vector has to be in the z direction. To calculate that, we go back to the original equation, and what we have is the partial derivative of b sub y with respect to x is equal to minus the partial derivative of b with respect to t. And take this derivative with respect to x, you get e sine omega t minus kx, and you get a minus and a minus k. And over here you had a minus, so this minus and that minus become plus. And if you move this dt to this side and integrate, you get minus k e sine omega t minus kx times the partial derivative. It's equal to the integral of dv. The integral of dv is b. When you integrate the sine, you get minus the cosine. And so this minus and that minus go out, and you get k over omega equals e cosine omega t minus kx. Omega over k is equal to the speed of light over 1. But k over omega would be 1 over the speed of light. So the magnetic vector is equal to the magnitude of the electric vector divided by the speed of light. Now there's one more part to this problem, and that is this. When you go to the beach, you can get a sunburn. So why are you getting a sunburn? Because the sun is hot. So if the sun is hot, it means that the electromagnetic wave is carrying power. So if we want to show what the power is in the electromagnetic wave, the power is equal to 1/2 E cross B divided by mu 0. And that has to have the units of watts per meter squared. So the electric vector has the units of newtons per coulomb. The magnetic vector has the units of Tesla. And mu 0 is Tesla meter per ampere. Okay? Now, if you divide coulombs by seconds, then you have to multiply by seconds. And so Tesla would go out, and this is an ampere, and so you have Newton meters per second, newtons per meter second. If you multiply by meters on top and meters on the bottom, you have joules per meter squared per second, and joule per second is a watt. So the Poynting vector, the electromagnetic field, is carrying power in watts per meter squared. Now to summarize, the electromagnetic wave propagates with the speed of light. The electric vector is perpendicular to the magnetic vector, which is perpendicular to the direction of propagation. And these waves carry power. Thank you very much.